Hi folks, welcome back. Today I would like to talk to you about something called property-based testing. It's a cool testing technique that I don't see used very often, but that I think could be very useful in a lot of contexts. So today will be a short introduction. We will not be deep diving, but we'll provide enough hooks to help you get started with this thing. Maybe before we take a look at properties, let's do a quick recap of what we do see a lot, and that is unit testing. So say I'm writing a function here, the sum function. I often write unit tests and they look something like this. You have assertions and you have examples, concrete examples. For example, 1 plus 2, or the sum of 1 and 2 should equal 3. And that's what we do when we write unit tests, right? We come up with examples and we encode them in automated tests, and if these tests fail, we know we broke something. It has its advantages because it's very clear, they're very concrete examples. People like to think in examples, so that is awesome, but it also has its disadvantages. And one of the disadvantages of unit tests is you have to come up with the cases. You have to think about all these different categories. I even have another video on it, on how to select or how to choose your next unit test, that goes a bit deeper into this topic. So you are expected to do the work as a developer or as an analyst or someone that's thinking about the problem. You have to come up with the different cases. And this is where property-based testing actually shines, because you still have to think a lot, you still have to come up with cases, but you can have the computer do so much of the work for you. So let's put property-based testing in contrast with unit testing. This is your very first property. Well, nice to meet you. This looks a bit different than a typical unit test, doesn't it? But it contains all the essential elements of these property-based testing libraries. So let's quickly go over what we're seeing here. Maybe to put it into words, what is a property? A property is something that should hold for your code given any random input of data. So you see here prop.forAll, that's saying I'm declaring a property and it should hold for all things. And what things? Well, that's the next line here. It should hold for all arrays of integers. So whatever array of integer we can think of, this property should hold. And this next thing, this arp.from, that's called a generator. So that's a way these libraries, these property-based testing libraries, provide building blocks so you can build random data, you can generate random data. And this is just a generator, that's a term for it, the generator to generate array of ints. So it should hold this property for all int arrays. And what is the actual property we're trying to express here? That's in this lambda here, this anonymous function. And this function, or this lambda, is saying whatever array of integers we have, this is the x's, this should return true. This property should hold. And what we're seeing here is if you take an int array and you reverse it and you reverse it again, that should be the identical array to the original. So that's the predicate or the property we're trying to define here. And that's how you define a property. And below here you do .quickcheck or .check. There's a lot of different methods here. But that's how you actually verify a property or run a property, how you would like to call it. But that's how you execute a test and say. So we have properties, we have generators, we have predicates to encode our properties, and we have a way to run our properties. These are the basic building blocks to work with property-based testing. So not too complicated, but it's very different from unit testing, right? You don't see any concrete numbers here. You don't see examples here. You see something else, something a bit more abstract. Now, what happens if you run this property? We hinted a bit at it a second ago, but it's working with random data, right? It's working with random integer arrays. So what the property-based testing library will do when it tries to verify this property, it will generate a whole lot of random integers and one by one feed them into this anonymous function, and it will try to find a counterexample. So it will try to find an integer array where this predicate will not return true, where it will fail. And if it has one, it says like, okay, I found a counterexample, this property does not hold, But if it generates 100, 1000, whatever integer arrays, and it returns true each and every time, that's when a property succeeds, or that's when this test succeeds. So it has tried with a lot of random data. It always turned out to be correct, so it marks it off as a success. And that's when you get the most satisfying message any lazy engineer would like to encounter. It's saying, okay, 100 tests passed. And that's what I love about property-based testing. It's such a nice trade-off. You think hard about a property, sure, and we'll go more into detail in that later, but you just write the one property and your computer will do the generation of 100 different test cases for you and run them. So that's pretty cool, right? So that was a quick theory and a quick dive into the basic building blocks or the basic principles of these libraries. And now let's take a look at code. Let's figure out some properties ourselves, right? It always helps if you have somewhat of a play problem to experiment with when you're learning stuff like this. And I chose the Mars rover Kata for this video. Mars rover Kata, let's do a quick summary. We're given, or we're a Mars rover on Mars, and we know about our location and we know about our direction, and we receive an input sequence of commands from planet Earth, and the input sequence can contain forward or back commands, so we move one space forward, one space back, or we can turn 90 degrees to the left or to the right. So we have 4 different commands. Let me grab the code quickly. It's not really important for today's video, but then we get an idea of the API we'll be testing, right? So we have our directions, just an enum. We have our locations, those are records containing an X and a Y coordinate. We have our enum that represents all the commands. And then we have our rover, and the public API of our rover is just one execute method that runs a sequence or an array of commands. And you can ask a rover, hey, where are you at? What's your location and what's your direction? So that's basically it. Now, so we have our problem domain and we have a basic understanding of what property-based testing is and what it should do. But how do you come up with these properties, right? That's the hard part. That's the tricky part about property-based testing. And there's a lot of blogs, videos, conference talks about this topic, actually. And I linked a couple below here, so you can take a more thorough look if you would like to. But I took my top 5 heuristics or top 5 rules of thumb to generate good properties, or to think up of good properties, and they're these 5. And let's quickly go over them one by one, and then let's just dive into the code and write properties for each of these 5 categories for our Mars rover. So what makes a good property? The first category of good properties is something I like to call, you can throw anything at it. And here you see Wonder Woman deflecting all the things. That's a bit what you try to test with these properties. Does my program deflect all the things? Does it handle any sequence of inputs? Does it handle any kind of commands you can give it without blowing up? So does it handle it gracefully? That's the first rule of thumb. Second one is different paths, but they all lead to the same destination. And this happens when you have multiple operations or multiple methods in your API. And you can kind of combine them or put them in sequence. For example, here you can increment every element in a list by 1, and you can sort a list. And if you do the increment first and the sorting second, you should end up with the same list as sorting first and then incrementing second. So that's leading to different paths that lead to the same destination, the second rule of thumb. The third one, it's a straight up Lord of the Rings reference. It's called There and Back Again. And that's when you have operations that are the inverse of each other. For example, when you reverse a list and you reverse that reverse list again, that's the property we saw a couple of minutes ago, you end up with the original list. And that's there and back again. Other typical examples are zipping a file and unzipping it again should result in the same file. Encryption, encoding, stuff like that all falls under this category. Or even something I use a lot is when you write something to a database and then later you read that same thing from the database, you should end up with the same record. So this is there and back again. Some things never change. I think it's the fourth rule of thumb. And that does not focus on whatever changes, but it focuses on the things that stay the same when you do something or when you run your code. For example, if you sort a list, the length of that list does not change, or at least not if you filter, don't filter any duplicates. But there's these things that do not change when you run your code. Like every element in the list should be in the resulting sorted list, stuff like that. I don't know. This is category number 4, I think. The more things change, the more they stay the same is another rule of thumb, and that's checking on, or that covers properties that cover idempotence. For example, if you have a sorted list and you sort it again, you should end up with the same list. And same with filtering, with message deduplication, stuff like that. So yeah, that was number 5. I'm sorry, I should have numbered these. But these are the 5 categories we are going to think about in context of Mars rover, and we'll write some properties. All right. I will be using FsCheck. It is a property-based testing library, originally from Haskell and then ported to FsCharp, but you can perfectly use it, or you can use it just fine in C#, which is what we'll be doing right now. So this is our example property we saw. Let me quickly run the tests to make sure that everything is green. Yes, it is. And I summarized those 5 rules of thumb again, so we don't have to switch back to the presentation every second. So let's take a look at the first category. You can throw anything at it. A good example of this throwing anything at it, and it handles it gracefully for our rover, would be that our rover, any random rover, should be able to run any random sequence of commands without blowing up. And that's an example of this rule of thumb. So let's try to write this property. Let me grab some code. And so what I said was any rover can handle any sequence of commands. That's what we would like to encode in a property, right? And as we said, a property has 2 different characteristics. One, it has ways to generate random data, and the other one is the predicate itself, or the rule we would like to check. So what do we need random data-wise? We need a rover. And how do you generate random data? You can do it with this arp.from. You'll see arp in FsCheck, but for all intents and purposes, and especially for today's introduction video, an arp or an arbitrary and a gen or a generator for random data generators, they are exactly the same thing. So don't worry too much about the arp letters. So let's define a generator that generates a random rover. A rover gen, and that is an arbitrary, the default arbitrary that for the rover type. And you can go crazy, and we will go crazy in a couple of minutes with these generators. We can combine them, we can build bigger generators out of small generators, but the defaults just create random data and look at the constructor and create random data for the inputs. So that's why the testing framework, or the FsCheck library, already knows how to generate random rovers in a one-liner. So that's pretty cool. So this generates random rovers, and that's not the only random data we need. We also need any random sequence of commands, right? So we can do commands, and that's the arbitrary for an array of commands. Array of commands without the generic things. There we go. So that generates a rover and that's a generator for random rovers, and that's a generator for any array of commands. Now, how do you debug arbitraries, or generators? Let me quickly grab one of these generators, for example, the array of command generator. Let me drop to an interactive window here, a script window, and let's play around a bit with this. So this is the generator. Command is ambiguous, I'm sorry. Let me namespace that. So this is a generator for any array of commands. And yeah, it's saying something, but so this is what, let me quickly grab this generate thing. This is a generator. How do you play around with it? Or how do you, when you're developing these, or you're writing these generators, how do you know whether or not it's a correct generator? Well, there's this sample function, You give it a size, which kind of dictates how big your randomly generated data is. For example, a list, it takes into account this size to encode random lists of a certain length, stuff like that. And we want 3 samples, so I want 3 random arrays of commands, and then you can take a look at the output here. And yeah, there are random arrays of commands. Some turn left, right, forward, back, and this is one of 7. There's a really short sequence of commands, so that appears to work. And that's how I typically debug or develop my generators, by taking a look at this sample function. Anyway, now we have a random generator for rovers and a random generator for commands, or arrays of commands. So let's feed these to the property. So for all rovers, randomly generated rovers, for all randomly generated sequence of commands, this property should hold. And this property is an anonymous function that takes a rover and a sequence of commands. And the property we were trying to implement here is any rover can handle any sequence of commands. So let's just take our any rover and run or execute this random sequence of commands. And that should not blow up, and not blowing up is the same as returning true for this predicate. So this anonymous function will return a rover, so it will return the end rover. And as long as it returns something and does not throw an exception, that's perceived as a succeeding property. So this should actually work and encode this first rule of thumb, or this first property, that a rover can handle any sequence of commands. And that's green, but we have not seen our test fail, so let's quickly inject a bug somewhere, maybe in the moving backward logic. Let's just swap x and y coordinates. So it's a bit of a hard to spot bug. So I hope the property will. Oh yeah, of course. I was thinking, I hope this property we wrote will catch it, but of course not. It's just checking that it doesn't blow up. So if we suddenly teleport to another location, this only single property we just wrote will not detect it. But we're checking whether or not it can handle any sequence of commands. If any sequence of commands crashes our rover, so our code explodes with an exception, that should actually work, right? So let me comment one of these cases. Yeah, let me comment going east once we're trying to move backward. I don't know if the property tastes first, or if it will catch it. Yeah, it catches it, cool. So we injected a bug, and this property fails. And I think this is the first time we see a failing property. So let's quickly pause and take a look at what that looks like. It's saying the property is falsifiable, so that means it generated a lot of random data and it found a counterexample where this property returned false or threw an exception, in our case, where the property did not hold. And it's giving us this seed, these random numbers here. That's something you can use to reproduce this exact same failure, this exact same random data generation. That's typically used when you're running these tests in a CI pipeline somewhere in the cloud, and you would like to troubleshoot a red test or a red property locally. You can just copy paste these random seeds, put them into your local test runner, and it reproduces the exact same random data and the exact same failures, hopefully. But what is this actually showing? So it was falsifiable. We found a counterexample, and it's saying, so given this rover and this sequence of commands, your property fails. And it says something about shrinking, but let's ignore that for now. It's just the smallest counterexample it could find. But yeah, you can find your counterexamples like this. So let's maybe undo our bug. Where was it again? There, we commented some code. And let's rerun our properties. Everything is green. We saw this test fail for the right reasons, so we are good to go. That was rule of thumb number 1, throwing anything at the problem, and we wrote our property for it. So let's take a look at the other ones. Number 2 is different paths should lead to the same destination. And let's not make it too hard. Let's just try to write a property that, given 2 very specific paths and given a random rover, does the rover end up at the same location for those two paths. So we only need a random rover. We don't need a random sequence of commands. Let's just zoom in on two very concrete sequences of commands. So the first sequence I would like to take, or I would like my rover to run, is hey rover, move up. So go forward, turn right, and then go forward again. So that's going, if the rover is facing north, it's going up, it's turning right, and it's going to the right. And I would like to state that, okay, where you run that now, so your location, your XY location, it should be the same as running these another path on this rover. So that should be, and let's now run another command on this rover. So rover.execute again. But this time not the forward, right forward, but let's first turn to the right and go the other way to end up in the same location. So first we turn right, then we go forward. Now we go left again. And then we go forward. That should end up in the same corner, right? The rover should be in the same XY coordinate. It will be facing a different direction. Now it's facing, I think, north, and in the first case it's facing east. So those will be different, but the locations should be the same. So that's what I'm trying to encode in this property here. There we go. So let's see if this works. Let's first make it compile. Different rover should end in same. So if we have mirrored paths that are like diagonally mirrored, then the rover should end up at the same. You can go crazy and think of some kind of algorithm to calculate mirrored paths, but we just hard-coded 2 there because we're just doing an introduction, right? But yeah, I think that should work. That should work. Let's quickly see where or not this fails if I remove one of the commands. It is. So yeah, I think this property holds, or that's an example of the different paths, same destination, but then in a very literal sense. We have literal paths and literal destinations. So that's more concrete than typically the case with these properties. Typically, you're not writing code to do pathfinding or navigation, but you can, as you can see. The third rule of thumb was there and back again, so that was unzipping a zipped file, stuff like that. Can we think of a case for a rover that falls under these rules of thumb, or this rule of thumb? And I think we can. If we have a path and we back up out of that path again, we should end up at the same initial location, right? And again, we can do a very complicated calculation to calculate the reverse of any path. That's probably very doable, but that would lead us a bit too far for today. So let's now just hard code 2 paths, or take very simple paths and verify this. So what is a very simple path? Let's make it a bit more difficult than just hard coding 2 paths, because then we won't learn anything new. Let's generate a random sequence of forward commands and then have the robot step backward the same number of times. So that's a bit more tricky than the second property we defined, but not going all the way with path reversal algorithms, stuff like that. So rover should end up in same location after retracing steps. That's the property we'd like to write now. So let's retrace our steps, or let's have the rover retrace its steps. We can go a couple of ways to have this random data, right? We can first generate random sequences of forward commands and then just deduct or figure out what the sequence of backward, or the length of the backward command should be. Yeah, that's actually, I have not tried that yet. Let's do that. So let's first generate a sequence of forward commands. And that's where we're going to need to take a deeper look at test generation or test data generation, because if I just would do arp to give me the generator for the command type, or the command enum, that will not work because that generates any command. And I want to have a specific command. I want to have the forward command repeated a random amount of times. So how does that work? Now we're going into the more complicated test data generation functions. And they're hidden in this gen namespace or this gen class. And you can do a constant generator. So that's the first one we'll see. And you can give it a value, any value, and it will return a generator that just always returns this constant value. So if I take a constant value of command forward, this is a generator that will generate forward. So that's not very interesting, right? But bear with me for a second, we're getting somewhere. I'm going to show you that you can build very complicated test data generators based on simple test data generators with some glue functions or combinators, if you would like. So this is a very basic generator that generates the forward command. Whoa. Now I want a list of these forwards. So I can use a function for that, some glue or a combinator, and it's called the list of combinator. And if you look at the signature here, it expects another generator as input. So if we feed it the forward gen, that generates the forward command. Now we have a generator that generates lists of forward commands, which is pretty cool. And you'll see in the type signature here, it's actually an F# list of commands, and that's not very helpful. So let's try to get rid of that by using some link syntax. I think that will work. Will it work? Yeah, it will work. There we go. So this from in, let's select the link syntax as we know it in C#. You can use that to transform and combine multiple generators as well. It comes from the functional programming world. I'm not going to go too much into detail, but it's a very elegant way to compose and transform generators. So that's the forward gen, let's call it F, so we don't confuse ourselves too much. And we just to-array that F# thing. And now this is a generator of command arrays, which is awesome. And this is a generator of command arrays that only contains forwards, right? And now we need to have the same sequence of commands or the same length of sequence, but not forwards. We want to have backs. How would we do that? Will we do it in the property or in the test data generation? Could go either way, right? I'm thinking, does C# have something called unzip? No, of course it does not. Okay, never mind. So let's write a forwards and back gen. To also have a list of back commands of the same length as this forward. So let's grab the forward from the forwards gen. So that's our command or our sequence of forward commands. And now let's generate a list that is as long as this, but only contains backs. And we can use enumerable.repeat to generate a list containing one element repeated a lot of times. And how many times? Well, it's the length of this forward list or forward array. So now if you take a look at the forwards backs gen, it returns a generator that generates tuples, one for the forwards and one for the backs. And let's also to-array this, so we stay in the array world. There we go. And that's the test data generator we can use to have our random retracing paths. So we have let's take a look at our property now. We have our rover. So for every rover and for every combination of forward and back that are balanced, so that are equally long. Something should hold, and what should hold? The forwards and the backs. Can I not deconstruct? Here's I can't deconstruct. That's a shame. I'm sure you can. I just don't know how to do it in C#. So what should hold in this case? Running. Oh, I know it's wrong already, sorry. I was getting confused about why this is not working. And it's not working because if you take a look at prop.forAll, it requires, or it takes arbitraries and not gens. And they're the same, but not the same. So I forgot about that. And this forwards backs gen, if you take a look at the type, it's a gen. The type is a generator. And this thing expects arbitraries. So you can do 2 arbitrary on a gen. It's not ideal because you lose shrinking, but yeah, never mind that. Let's continue. So now we have forwards, backs, right? Can I now deconstruct into forwards and backs? I cannot. That's a shame. So yeah, let's take the forwards and the backs and execute the forwards first, and then execute the backs first, second. There we go. If any of you viewers knows how to more elegantly deconstruct this tuple, please leave it in the description below, because I don't write this this kind of C# every day. But anyway, so we have a generator that generates random forward sequences, and now we have a generator that also calculates the retracing path, so the backward steps. So our rover should end up in exactly the same location. Exactly the same direction, and it appears to work. Maybe to see it fail, let's, instead of having it go forward and back, let's have it go forward and forward so we can see it fail. It's not failing. That is interesting. Oh yeah, we should assert something, right? So it should be the initial rover. There we go. Now I expected to see it fail. So if you're not writing your tests before, always watch your test fail, because bugs like this, they creep up on you. Even when you're writing properties. Now everything is fine, everything is green, and we have our third property of the rule of thumb there and back again. So as you can see, it's getting a bit more complicated with the random data generation. Not so much the defining the properties, but the random data generation. Let's push through. Let's do these 2 last. So we have from very simple to very complicated properties. We've seen some of those. So for the 4th category of rules of thumb, we have some things never change. And can we think of some properties falling in this category? I think so. What never changes for our rover? Well, depending on the commands we send it, some things should not change. For example, if I have a rover and I move it forward and backward, whatever, as we've been doing in the previous property, that should never change its direction. Or vice versa, if I start rotating left-right, that should never change my location. And that's a property of that category. I'm thinking, will we learn something new if we type it out? I don't think so. No, let's leave that as an exercise to you, dear viewers, to encode that property. So the property state, the property I would like you to take a look at is moving forwards or backward in any amount of forward-backward commands should not change the rover orientation. So have fun with that, and we'll take a look together at number 5 here. The more things change, the more they stay the same. And that rule of thumb was what does not change, or what stays the same when you, what stays idempotent, right? And I think we can come up with something of an idempotent sequence of commands. We've seen one before, this path thing, but I think there's another cool one. where you have a single sequence that will always result in the same end result, and that's doing 360s. If a rover does a 360, or if a simulated rover at least does a 360, it should end up in the same location. If rovers on Mars started doing donuts and 360s, I don't think if that would be very idempotent now. So let's keep it to our simulated rovers. So that's an example of these. Some things never change. 360 should not change the rover. Will we stay with one 360? Let's go out with a bang and let's make it complicated. So a series of 360s. No matter how many 360s we do with our rover, it should always end up at the same location, in the same direction, right? So let's think of a way to do the 360 test data generation, because doing the property, writing the property, will not be very hard, actually. We already have it down here, I think. So that will be okay. But let's think about how we would generate random commands that represent 360s. And then we'll be able to show some more complicated generation or combination of generators magic. So how do we generate a single 360? A single 360 is a sequence of 4 left commands or a sequence of 4 right commands, right? So we can do a sequence of 4 left commands. That's 1, 2, 3, 4. So this is one 360 in one direction. I'm getting my parentheses mixed up. So that's in one direction, but I want a 360. Any 360 will do, so also the right variant. And there's a combinator function called choice, or that's not choice, one-off, I think. If my hands would help. Okay, so there's this one-off combinator or glue function, and that takes a list of generators, and it will just select a random value for one of those generators. That's exactly what we need for our 360s. So we're stating that give me one of the 4 left turns or one of the 4 right turns. And that should be a 360. There we go. So this is a generator that generates an array of commands, and every array of commands should represent the left or the right 360. That's one, but I would like a whole lot of 360s, right? That would be way cooler than just doing a single donut spin. So how do we do a 360s multiple generator? We've seen that. There's this list of glue function, and we can give it to the 360 gen. And then again, it's that F-sharp list instead of an array in a C-sharp array as we know and love. So let's do the link magic again. And now we have a generator that generates lists of commands, because every 360 represents a list, and we have a list of 360s, so it's a list of a list. But my rover does not speak list of lists, it speaks a list of commands, or array of commands, sorry. So how do we flatten this list again? Especially when it's a generator and it's not just a list? Well, we can use this link syntax again. So our flat 360s generator is grab whatever is in that 360s gen. And we want to flatten that. And flattening a list, you can do it, for example, by doing select many and just returning the values. So if you take a look at what we're returning here, it's a gen of an IEnumerable of commands. I don't like IEnumerable, so let's to-array it. And now we have a generator of arrays of commands, and that's exactly what we want. So I think we have our 360 generator up and running. And you see, again, it's getting a bit more complicated. There's a bit more glue functions in there. And there's a bit of complicated link stuff, but once you get the hang of that, this is very fun to write. No, I want the flat 360s gen, sorry. And this is my sequence of 360s, yes. And if we write this property now, whatever random rover, whatever random sequence of 360s encoded in a single array of commands, if we execute these sequences, the rover should remain stationary in exactly the same location as it started. And that appears to work. Let's introduce a quick bug. No, let's just introduce a quick bug into the generator. That will also work. Okay, so yeah, it fails. It provides correct feedback, so I think this works. And that's an example of the more things change, the more they stay the same, or idempotence category. And that's all I have for the coding part. So writing good properties, not that easy. And it's a bit tricky with the link syntax. But if you like stuff like that, this is a really elegant way to write properties. I had some summary things. Yep, there we go. So time for a recap and some conclusions. What did we learn today? We learned that property-based testing libraries, they offer us building blocks to generate random data, and on the one hand, and on the other hand, to verify properties or to try to come up with counterexamples for the properties you define. Random data is generated by these generator functions or by the glue functions, which are called combinators. And properties always have the same kind of form. They always have this for all random data of this type, random data of that type, this predicate or this true-false statement should hold. And what these libraries do is they generate a lot of random data in the way you define in your generators, and they run the predicate against it, or they feed it to your predicate, and they try to come up with a counterexample, right? I think the summary for property-based testing is it's very hard to come up with good properties, so you need some rules of thumb like we discussed. You can throw anything at it, so program handles it gracefully. Different paths should lead to the same destination is a good one. There and back again, where you retrace your steps. Some things never change, some properties stay the same when you run your code, and the more things change, the more they stay the same. That's the idempotence thing. And if you use these rules of thumb on your problems, I'm pretty confident you can come up with some really cool, really interesting properties. To go out, I have a quote from Jessica Kerr's blog on property-based testing, or I have two quotes actually, and I love that post. Make sure you read if this sounds interesting at all. But let's quickly pause at these quotes, because they're very true. See how much thought goes into a property-based test. And this is a simple example. Mars rover also, very simple example. I don't recommend writing properties for all your code, only the really important stuff. So it is hard to write properties. It's hard to do property-based testing. So only use it when it matters. Only use it when you're sending people to the moon, metaphorically speaking. Not when you're testing getters, setters, or a controller routing, stuff like that. Second quote, property-based tests are best combined with example-based tests. So the example-based tests are unit tests. So it's not an or kind of thing, it's an and thing. Examples help you start organizing your thoughts, and they're easier for future you to read and understand when you come back to this code later. Humans think in examples. So humans are helped a lot by unit tests. But programs, they have raw computing power. So if you augment your unit tests with these randomly generated verifying properties, that's something a computer is very good at. So use both. Math, it's a tool. I love that end quote. So it's not an or thing, it's an and thing. And it's really hard, so don't do it for all your code. That's my executive summary of property-based testing. And to go out, I would like to propose a challenge to you. You've seen me play around with this in C# and .NET on some toy problem. I have a workshop on this, so I have some code for the exact same problem for the Mars rover on this bit.ly link here. I'll put it in the description below. And play around with it. See what properties you can come up with. Let me know in the comments below if you found out some cool properties, or if you figure out, find some new rules of thumb, some new heuristics that I didn't list, I would be very happy to hear them. And once you got your feet wet with this property-based testing, maybe you can use it on your own projects. Maybe you are writing complicated stuff. Maybe you are sending people to the moon. And I would be very interested in hearing that. That was all I got. This was property-based testing with examples in C#. I hope you learned something new. I hope you had fun. See you next time. Bye-bye.